Molecular diffusion models are the standard for 3D generation, but they suffer from a critical bottleneck: no principled signal for sample quality. When scaling generation budgets, you're left with chemically invalid or unstable outputs, and relying on the model's own likelihood is risky because these scores are often poorly calibrated. A recent study introduces a post-hoc uncertainty estimation framework to solve this. The method fits a Laplace approximation to the pretrained denoising network. To scale to high-dimensional models, they apply the approximation to the final layers and use the empirical Fisher as a Hessian approximation. This constructs a Gaussian posterior centered at the map estimate. During sampling, they leverage this posterior to quantify uncertainty. For a subset of time steps, they draw M-weight samples from the posterior and compute the corresponding noise predictions. They define the intermediate uncertainty as the element-wise sample variance of these predictions across the weight samples. Finally, they aggregate this variance over the time step, atom, and feature dimensions to yield a single scalar uncertainty score per molecule. The core hypothesis is that low-quality samples induce higher variability in the denoiser's trajectory. Empirical results on QM9 confirm this. The uncertainty score exhibits a strong negative correlation with stability and validity metrics, outperforming the diffusion negative log likelihood baseline. For example, uncertainty achieves a Spearman correlation of -0.284 with molecular stability, compared to -0.15 for NLL. This correlation enables test time compute scaling. By generating a larger batch and filtering to the lowest uncertainty samples, they demonstrate significant quality gains. Oversampling and filtering improved molecular stability by approximately 10% without retraining the generator. However, the method has limits. It fails to transfer to the more complex GEOM drugs dataset, and ablation studies reveal that replacing the Fisher-based covariance with an isotropic Gaussian yields nearly identical results. This suggests the signal is driven more by model sensitivity to parameter perturbations than by true Bayesian epistemic uncertainty. Despite these caveats, this post-hoc score provides a drop-in verifier for test time scaling, offering a practical lever to improve molecular generation quality at inference.